Very well. Let us continue chapter 5. What we learned so far. Let's recall. Recall that we start talking about Riemann sum, and then we take the limit of our Riemann sum and we define something that we call the integral. So the Riemann sum, remember that this ugly sum f sigma of f of x of I delta x. I starts from 1 and goes to n, and then we take the limit of this sum while n goes to infinity. Remember the reason for that? You're trying to make those subintervals very small by sending n to infinity. We call that again our delta x was b minus a divided by n. This limit is equal to, so instead of keep saying that, hey, we have the limit of Riemann sum, we're coming up with a new symbol, the integral of function f with respect to variable x while x changes between a to b. Well, okay. We started by talking about the area, but integral has many different interpretations in different disciplines. Well, we also learned that if we have some properties, if we have the integral of f of x plus g of x with respect to variable x, denoted by dx, a to b, remember that they call it definite integral. We can just split these into separate sums or separate differences, f of x dx plus the integral a to b gx dx. You can generalize the idea. Suppose you have n different functions, n terms, you can just calculate each of those integrals separately, and then you add the results together. We also learned that if f is symmetric function, we're talking about these nice functions. We don't keep saying that, hey, f is nice function. What do I mean by nice function? It means that it doesn't have that many discontinuity. So imagine you have a nice function. So if for f to be symmetric with respect to y-axis, remember that the integral negative a to a of f of x dx is equal to 2 times. Now we change the lower bound to the 0 and the upper bound stays the same as a f of x dx. We're going to come up with more nice properties for integrals, but first let us define some new formulas that helps us to calculate the integral and feeling comfortable about calculating definite and indefinite integrals. One of them that you learned was using, for example, a polynomial functions, quadratic functions, and so on. So techniques of integration. In techniques of integration, what are we using? We are using the fundamental theorem of calculus. Fundamental theorem of calculus tells us that if f is a continuous function, if f is a continuous function, over interval, closed interval, a and b, then function g of x can be defined this way. Function g of x is equal to the integral a to x of f of t d of t. And your t ranges between a to x, and x is bounded between a and b. So what we defined a function which is the integral of another function. Well, okay. Remember that when we defined a function in pre-calculus, in intermediate algebra, then we moved on to elementary calculus, we're interested in finding the derivative of this function. So I expect you to ask, you defined a function, what is the derivative of this function? The derivative of this function, g prime of x, is equal to, well, remember that integral, or what you learned previously, antiderivative, is the opposite of derivative. So in a sense, when you're taking the derivative of this integral, the derivative and integral, they cancel out each other. When they cancel out each other, you have f of x. So this actually helps us to make sure when we are defining the integrals of functions, we have a correct integral. What do I mean by that? Take a look at this. What we defined before, we said that, hey, if I have the integral of x to the n dx, this integral is equal to, we take the exponent, we take the power, we have x raised to n plus 1, we add 1 to the power, divided by this new power n plus 1. And we add a constant like c, and we call it the constant of integration. Okay, take a look at the fundamental theorem of calculus. It says, hey, if f is a continuous function, so x to the n, and suppose n is just a nice exponent. Well, this guy is f of x. This is on the right-hand side is your function g. So if I take the derivative of function g, it must be equal to x to the n. So let's take a look at this. This is your function g, g of x, and this is your function f. Let me use a different color for this. F of x. So fundamental theorem of calculus says g of x is equal to the integral of f. So g prime of x must be f itself. So what is g prime? Let us take a look at the derivative of g. So remember that when you have a function, a variable raised to an exponent, when you are taking the derivative, you are reducing the exponent. So it is equal to, well, here you have n plus 1. We drop the exponent. We take 1 unit out of the exponent. So x to n plus 1 minus 1. And on the denominator, I have n plus 1. So I'm going to copy down n plus 1. And since you have c as the constant, the derivative of constant is just 0. So on the right-hand side, the derivative of g, if I cancel out these two, is going to be x to the n. 1 minus 1 is equal to 0. Is it equal to f? Of course. You just write, see this here. F of x is equal to g prime of x, which is x to the n. So fundamental theorem of calculus help us to make sure we have a correct g of x, which is related to the integral of f of x. So let us introduce more formulas, more techniques. More integrals. Very well. So what is the integral of a constant? K dx. So k is just a constant. The integral of k dx is equal to k times x plus c. Again, we can apply fundamental theorem of calculus to make sure that we have a correct formula. Here you have your g of x, and on this side you have your function f. If I take the derivative of g prime of x, it must be equal to my f. But g prime of x, the derivative of kx is just k. The derivative of constant is 0, which is equal to k, which is equal to f of x. Okay, we're happy about this. Next. The integral of e to the x dx. And I'm going to generalize this formula for you. So you see if in general we have exponent n, what happens? So the integral of e to the x dx happens to be e to the x plus constant c. Again, make sure you are verifying the equality between g prime and f. So here you have your g of x, and here you have your e to the x, the exponential function. So g prime of x, the derivative of e to the x, you all know that is e to the x, plus the derivative of constant 0, which is equal to, of course, e to the x, and e to the x is our function f of x. Okay. Now I expect you to ask, what if I have the integral of e to 2x? What if I have the integral of e to 5x? What if I have a number multiplied by the exponent? Do we have a general formula for that? So in general, we can say that if we have the integral of e raised to nx dx, it is equal to e to nx divided by n plus constants. This is more general than the integral of e to the x dx. Again, you can verify that. This is your gx, the derivative of gx, e to nx, and e to nx divided by n and n get canceled out. So you get your e to nx. What about trig functions? The integral of sine x dx is equal to actually negative cosine x plus constant of integration. Again, we can verify that gx, and this is our f of x, the derivative of g is equal to, so we have a minus sign, and the derivative of cosine is negative sign. So we get two minus signs. The derivative of c is just 0, so it is equal to sine x, which is our f of x. Again, I expect you to ask, do we have a general formula for that? If I'm going to take the integral of sine of n times x, suppose you have a number next to your x. So in general, we can say that, well, the integral of sine nx dx is minus cosine nx divided by n plus c. More general than sine x. When you have sine x, it means that n is equal to 1. Well, what if you have cosine? The integral of cosine x dx is sine x plus constant of integration. Why is that? The derivative of sine is cosine, which is equal to your function f, which is cosine. All of these can be verified using fundamental theorem of calculus. Okay, so g prime of x, the derivative of sine is cosine, which is equal to function f of x. So again, we can generalize this formula and have the integral of cosine n times x dx equals to, so here you have sine nx divided by n plus constant c. Well, let us make it more interesting. So the integral of dx divided by x, or the integral of 1 over x dx is equal to, this is equal to the ln function. So it is ln of absolute value of x plus constant of c. This is your function g. You want to show that the derivative of function g is equal to function f, which is 1 divided by x. Okay, let's verify that. G prime of x. So what you learned before about ln, you know that the derivative of ln of x is equal to 1 divided by x. So here you have 1 over x, and the derivative of c is just 0, and it is exactly equal to function f of x, 1 over x. The integral of b to the x. Suppose we have an exponential function and the base is not e. The base is just b. B to the x dx. Well, this integral is equal to b to the x divided by ln of b plus constant of integration. again, let us verify this. Here you have your function g. And here you have your function f, b to the x. Okay, the derivative of g prime of x. First of all, remember that what you learned in elementary calculus is when you have an exponential function b to the x, the derivative is b to the x times ln of b. This is what we learned in elementary calculus, taking the derivatives. So here you have the derivative of g. So the derivative of b to the x is just b to the x times ln of b. On the denominator, you have a number. So it means that you have 1 divided by ln of b. If you use your calculator, you can find that number. In this case, just copy down ln of b, and the derivative of c is just 0. You can simplify this guy. It is equal to b to the x, which is nothing but f of x. Okay, perfect. The integral of secant squared of x dx. It is equal to tangent x. Tangent x plus constant of integration. Okay, you're getting back to pre-calculus, trig functions. Here we have our function g of x, and here you have your f of x, secant squared. Okay, so g of x, you're taking the derivative of g. G of x is equal to tangent x. Remember that tangent was sine over cosine. Here you have constant c as well. So now when you want to take the derivative of g, you're actually applying the quotient rule. G prime of x, the derivative of sine times cosine. So the derivative of sine times cosine minus the derivative of cosine times sine. Sine x times the derivative of cosine. Everything is divided by our denominator raised to the second power. Okay, so g prime of x is equal to the derivative of sine is cosine, cosine times cosine, you get cosine squared, minus sine times the derivative of cosine. The derivative of cosine is negative sine, negative times negative gives us positive, and we have sine squared. Divided by, okay, the denominator is just cosine squared of x. We know that sine squared plus cosine squared is equal to 1, so we have 1 divided by cosine squared of x, but 1 divided by cosine is nothing but secant. That's how we define secant. Since secant of x is 1 over cosine of x, we know this definition, this guy is equal to secant squared of x, which is equal to f of x. We verified that the integral of secant squared dx is tangent x plus c. Very well. So now, what about the integral of cosecant squared? The integral of cosecant squared is negative cotangent x plus c. Cosecant squared of x dx is negative cotangent x plus c. By the same method, you can take the derivative of negative cotangent and show that the derivative of negative cotangent is equal to cosecant squared. Now the integral of secant tangent. the integral of secant x tangent x dx is equal to secant x plus c. The same approach, here you have your function g, and here you have your function f. By taking the derivative of g, we show that it's equal to f. So g prime of x, this is secant. Secant is 1 over cosine x. So here you have negative the derivative of cosine x divided by cosine x squared. And here you have, this is going to be sine x divided by cosine squared of x, which is sine x divided by cosine x times 1 over cosine x. So this is just tangent of x, and this is 1 over cosine, which is secant x. This is your function f. The derivative of g is equal to f. Well, what if we have the integral of cosecant cotangent? Now it's going to be negative cosecant of x. The integral of cosecant of x, cotangent of x, dx is minus cosecant of x plus c. With the same approach, same method, taking the derivative of right-hand side is equal to function f. I'm going to write down 4 more formulas for you. Then we're going to go over some examples. So the integral of dx over 1 plus x squared is equal to, here you have your inverse tangent or arctangent of x plus c. Then the integral of dx over square root of 1 minus x squared is inverse sine or arc sine. Then the integral of hyperbolic functions, the integral of hyperbolic sine x dx is hyperbolic cosine x. And finally, we have the integral of hyperbolic cosine dx, which is equal to hyperbolic sine x plus c. Okay, some nice examples. Let us write down some examples here and try to solve these. The very first one is what is the integral of dx divided by x, and what is the definite integral 3 to 6 of dx divided by x. Next one. What is the integral 0 to pi over 2 of cosine x dx. The next example, what is the integral of x squared minus 2x plus 5? Remember that we need to have dx. We need to make sure we are taking the integral with respect to variable x. And another one, what is the integral of 10x to the fourth minus 2 times secant squared of x dx. And the next one, what is the integral of cosine theta divided by sine squared theta d theta. Very well. So what we learned here, we know that the integral of 1 over x dx is ln of absolute value of x plus c. If x is positive, we don't care about that absolute value anymore. So take a look at this case. Here it is equal to ln of absolute value of x, and x ranges between 3 to 6. They have a definite integral. So it is equal to ln of 6 minus ln of 3. But what we learned before in intermediate algebra is that it is equal to ln of 6 divided by 3, or it is just ln of 2. So this definite integral is equal to ln of 2. The integral of cosine is sine. So we have sine of x. X ranges between 0 to pi over 2. So we have sine of pi over 2 minus sine of 0. Definite integral. Remember that sine of 0 is equal to 0 and sine of pi over 2 is equal to 1. So this area below the function cosine x, when x is bounded between 0 to pi over 2, is equal to 1. So let us write this right here in this little box. So you know that we use the integral of cosine x dx equal to sine of x. Now for d, it's not that hard. Here you have x to the second power. Remember that. Then we have power functions. The integral of x to the n dx is x to n plus 1 divided by n plus 1 plus constant of integration. So the integral of x squared is going to be x cubed divided by 3 minus 2 times. Here the invisible exponent is 1. You get x squared divided by 2 plus 5. It doesn't have any x next to it, but what's the meaning of that? It means that you had x with exponent 0. So you have 5 times x to the first power divided by 1 plus constant of integration. So of course we can simplify this. We get x cubed divided by 3 minus, we can cancel out 2 and 2, x squared plus 5x plus c. Let me move f a little bit here. I need more space for e. So you have this term, which is 10 times x to the 4th. The integral of 10 times x to the 4th. 10 is just the coefficient. So we're going to copy down the coefficient here. Then the integral of x to the 4th is x to the 5th divided by 5 minus 2 times the integral of secant squared. So what we learned about secant squared? When we have secant squared, the integral of secant squared is nothing but tangent. So 10 x to the 5th divided by 5 minus 2 times tangent x plus constant of integration. You might say, hey, we have 10 divided by 5. You can simplify this, of course. So you get 2x to the 5th minus 2 times tangent of x plus c. So as you can see, as long as you know the integral of secant squared equals to tangent of x, you don't have to apply the fundamental theorem of calculus to make sure that is the correct integral. So the integral of secant squared is equal to tangent, and we just copy it down here. Very well, let us take a look at this one. Let us try to simplify this first. Here I have the integral of cosine divided by sine times 1 divided by sine. Okay, and this is the theta. Very well. So I have the integral of cotangent times cosecant d theta. And since they have the integral of cotangent, cosecant, we just learned that this is equal to minus cosecant of theta plus constant of integration. Can you repeat your question?
I didn't see the recording before. But it's just,
The recording?